So today I'm going to be doing another circular polarization problem, and the problem is as follows. A right-hand electromagnetic wave is propagating in the negative x direction in a lossless medium of epsilon r is equal to 4 and mu r is equal to 9 at a frequency of 1 GHz. The electric field amplitude is 5 volts per meter along the z-axis at t is equal to 0, and it's asking us to write an expression for the electric field and the H field. So, just to get things started, I'm first just going to draw what we know. So, we know that it's propagating in the negative x direction. All that means is it's giving us the direction of our k for our incident wave. So, I'm just going to draw it first. Draw my axes, and I think I'm going to be drawing it in this direction. I will label this axis x, and then this axis z. But you can draw it however you like as long as you stay consistent with your right hand rule. So, where is my y? Well, x, y, and z. So that means positive y is coming out of the page. So write this down for reference. So, we know that it's propagating in the negative x direction. That means our k will be going this direction. K, I. Then, it's also saying that electric field amplitude is 5 volts per meter along the z-axis. That means it will be going this way, which will represent our E. So now the question comes, and what is our H? What direction is our H? Well, we're going to choose right hand rule. So, pointing my thumb in K and my fingers on E, my fingers curl out of the page. So, that means it's coming out of the paper. And this will represent our HI. Then the same can be also done for transmitted and reflected, but because it's not asking for that in this problem, I won't do it. So now let's just begin writing our E field equation. Well, just to make things easier, I will just write what we need for our E field expression. So we need our direction, our magnitude, and then also the phase, and then the units, and we know the units is watts over meter. So that means our E will simply be equal to the direction, which we know is going on the z direction, which is shown in this diagram and also said in the problem, along the z-axis. So that's the direction is z hat times our magnitude, which is 5 volts per meter, times 5. And because it's saying that we have some sort of non-zero at time equals to 0, we know that this phase will be cosine times omega. In this case, omega can be found by using the frequency of 1 GHz. So omega is simply equal to 2 pi f, or 2 pi times 1 times 10 to the 9, which is the gigahertz, which is a gigapart. And I will just leave this as omega just to make it look nicer. So it will simply be 2 pi times 10 to the 9 t plus, well, we don't know the direction, but plus or minus our k. So if you look at a direction of k, it's heading towards the negative x direction, right? So that means if it's negative, all that means is we have to swap the sign when it's inside this phase. So it will be positive x direction. But then what is our the magnitude for k? Well, since we know omega, we can use that to our advantage. We know that omega is equal to Vk, and we're not using Ck in this case because it is not in air or vacuum. Then solving for k, we get k is simply equal to omega over V. Then we need to take into consideration of our epsilon r and mu r. Usually we treat epsilon r as 1, but in this case we cannot do that. So how do we take that into consideration? Well, a more general form of V, if you don't know, is equal to C over mu r epsilon r. So if you plug this in and simplify it, you will simply just get omega over C times square root of mu r epsilon r, where mu r simply represents the relative magnetic permeability, and epsilon r is just the relative electric permeability for the material that we're working with. So plugging in our numbers, we get k will just be equal to 2 pi times 1 times 10 to the 9 over 3 times 10 to the 8 times the square root of mu r, which is 9, times epsilon r, which is 4. And doing the math, you will get 40 pi. Now this is simply just going to be a magnitude for k. And we know, as said before, it's going in the negative x direction. So it'll be 40 pi x. So I'm going to just call this E1 just to make things a little bit more simpler. And I'm out of room. So we still need to take E2 into consideration. Well, I'm just going to write E1 again. And E2 in this case, if you look at our diagram, well, if we look at our diagram, we know that the electric field amplitude is on the z-axis. So, finding the direction, I will just redraw it just to make it easier to see. So, if I redraw my electric field again, and we know that E1 is at z, and if I call this z right here, and y, this simply represents the electric field at time is equal to 0. So where is our x coordinate? So x will simply be out of the page, and y is here, like I said here. So x is coming out of the paper. That means k is going in, because it's positive x, we need to switch the sign, so k is going into the paper. So doing our right hand rule, because it's right hand circular polarization, we're going to find where E2 direction is going to be. So pointing my thumb in the direction of k, and laying my fingers at where E1 is, my fingers will curl towards where E2 is going to be. And in this case, it's going towards y. And that's simply going to be our direction. So, y hat times the same magnitude, but this time our phase will be sine, and everything inside will be the same. 2 pi times 10 to the 9 t plus 40 pi x. That means our E will simply be, copying these two together, we simply add E1 and E2. Z hat 5 cos 2 pi times 10 to the 9 t plus 40 pi x plus y hat 5 sine 2 pi times 10 to the 9t plus 40 pi x. And this is part of our answer. So now to find the H field. So finding the H field, we'll draw a line right here. You know that this equation will consist of a direction, magnitude, phase, and a unit, which is simply going to be amps over meters. So let's just first find the magnitude. So we can use the relation of E naught over H naught is equal to eta. And the reason why we are using eta and not eta naught, again, is because we are working with a medium which is not in vacuum or air. And just remember, eta is simply equal to mu over epsilon, where mu is the magnetic permeability and epsilon is the electric permeability. Now, just to make this more clear, we know that the magnetic permeability is equal to the relative magnetic permeability times the permeability, or mu naught, that is concerned with air or vacuum. And same can be said with the electric permeability, which is epsilon r and epsilon naught. And then we know that the square root, this portion, is simply equal to eta naught. Which is 377 ohms. So that means that we simply have eta naught times mu r over epsilon r. So finding our eta is simply going to be 377 times the square root of mu r over epsilon r. And the problem states that our mu r is simply going to be mu r is 9, sorry about that, divided by 4. So that means our eta is just going to be 565.5 ohms. So again, the reason why we're doing all this work is because we need to deal with the relative permeabilities that are given to us in the problem, or mu r's and epsilon r's. So I'm going to solve this on the next page. So we know E naught over H naught is equal to 565.5 ohms. And our epsilon naught is simply going to be 5. So 5 divided by H naught is equal to 565.5 ohms. Solving for this, you figure out that H naught is equal to 0.0088. So now we have almost everything to solve our H field equation. So I'll just write down what we know. Our H field is simply going to be the direction, which we have not figured out yet, but we have, but a magnet times a magnitude. So, to find a direction, we can just look back at the diagram that we drew. So, this diagram states that H is going out of the page, and that said that Y is going out of the page. So that means that H is going in the positive Y hat direction. So, this will be Y hat and times cosine, because we know at time is equal to 0, it's non-zero. And everything else can be the same as we wrote down before for the E field, which is 2 pi times 10 to the 9t plus 40 pi x. Plus our H2. So what direction will our H2 be in? Well, I'm just going to redraw it to make things easier to see. So if I label this my Y, then I know this is where our H1 will be at time is equal to 0. And then I would simply just label this as our Z coordinate. So that means that our X will be into the paper because X, Y, and Z. So X is into the paper, then that means K is in the negative X direction, so it's coming out of the paper. So using my right hand, because it's right hand circular polarization, we can find the direction that H2 is heading to. So putting my thumb in the direction of K, which is coming out of the page, and putting my fingers on where H1 is, it will curl towards H2. That means H2 is going to be in the negative Z direction. So it will be in a negative Z hat times the same magnitude, 0.0088 times the same thing, but it will be sine, times 2 pi times 10 to the 9t plus 40 pi x. And this will be our expression for our magnetic field. So just to reiterate, this is our expression for the E field, and this is the expression for the H field.